Hi everyone, this is the first lecture of the fourth week and we're going to talk about the multiple regression. Here's an outline of the lectures this week. First, we're going to talk about multiple regression and OLS model. And then the second lecture will discuss the measures of fit, particularly adjusted R-square. And then the third lecture will discuss least squares assumption, especially on focusing on multicollinearity. So here's a population multiple regression model. A lot of the terms are basically the same as a simple linear regression. So here we're considering the case with two regressors, but multiple regression model can include any number of regressors. Same as the simple linear regression model, y is called the dependent variable and x1 and x2 are called independent variables or regressors. yi, x1i, x2i represents the ith observation. So when you have a sample, it'll be the first observation or second observation. And beta 0 is an unknown population intercept. So it is when x1i and x2i's are 0, that's when you get beta 0. Beta 1 and beta 2 have slightly different meaning from simple linear regression. In simple linear regression, we say beta 1 is the effect of a change in x1 on y. But since in this case, in multiple linear regression model, we have more than one regressor, beta 1 is the effect of change in x1 on y holding x2 constant. In other words, how much does y change when x1 changes by 1 unit, holding x2 constant? And beta 2 has a similar meaning, just the other way around. So beta 2 is the effect of a change, or how much y changes when x2 changes by 1 unit, holding x1 constant. Sometimes we say holding something constant as controlling for something. So in this case, we can say beta 2 is how much y changes when x2 changes by 1 unit, controlling for x1. UI is the regression error, or in other words, omitted factors. And in previous lecture, we talked about omitted variable bias, which is a special case. So UI contains all the factors that can affect yi that is not included as independent variable. I'm a little careful to say the effect. We have discussed this in the previous lecture. What does it mean to be causal? And sometimes it's hard to say it's causal effect because there's a, for instance, omitted variable bias. But in this case, when you're just talking about UI in general, it's any factors that can affect yi that is not included as independent variable. Omitted variable bias is a special case. So omitted variable bias, in order for omitted variable bias to occur, you need to have two conditions. Not only does something that is missing, not included in the model, has to affect y, but it also has to be correlated with one of the independent variables. If those two conditions are met, then we consider it as having an omitted variable bias. So if you don't remember the details, you can refer back to the previous lecture. So similar to the simple linear regression model case, we don't know the population regression model, so we need to use OLS to estimate these parameters that we don't know, such as beta 0, beta 1, and beta 2. Here's a mathematical way of interpreting each coefficient in multiple regression model. So let's go back to our previous problem of trying to understand the relationship between the test score and student-teacher ratio. In our case, test score was our dependent variable and student-teacher ratio was an independent variable. We also said that the percentage of English learners we believe that's one of the factors that can impact the test score. Now let's say that we want to know what is the impact of changing student-teacher ratio by a certain amount. Say we want to increase student-teacher ratio by 2, how that impacts the test score. This may go up or go down, we don't know, but we believe that it can impact the test score. We also want to keep the percentage of English learners as constant, so we don't want to change the percentage of English learners. So here's an equation before and after we change the student-teacher ratio by a certain amount. If we subtract one equation from the other, if we take a difference between before and after equation, here this term will become beta 1 x1 plus beta 1 change in x1. And if you take a difference, most of the terms cancel out. So y cancels out, beta 0 would cancel out, beta 1 x1 will cancel out, and beta 2 x2 cancels out. So what's remaining is change in y is equal to beta 1 change in x1. If you divide both the left-hand side and right-hand side by change in x1, then all you have remaining is beta 1 is equal to change in y over change in x1. So since we only changed x1 and not x2, this could be interpreted as beta 1 is how much y changes when x1 changes, holding x2 constant. This is the same thing if you solve the equation. If you change the x2 by a certain amount and you don't change x1, then that is an interpretation of beta 2. So beta 2 is change in y when x2 changes by a certain amount, holding x1 constant. As I mentioned before, beta 0 is when x1 and x2 values equal 0. Now let's talk about the model using the actual numbers. In the simple linear regression case, we said that test score is only affected by student-teacher ratio, and we estimated these coefficients using OLS. We also now believe that the percent English learners in the district, or this variable called percent EL, actually also impacts the test score in addition to student-teacher ratio. Estimating this model in Stata is very simple. So it's the same as a simple linear regression. You use this command regress, and test score are dependent variable and 2 independent variables. Once you put in this command, Stata would spit out these outputs, giving you the coefficients for beta 0 as well as beta 1 and beta 2. So now we have simple linear regression model where you only have student-teacher ratio as an independent variable, and multiple regression model where you have student-teacher ratio as well as percent English learner as independent variables. You notice that the coefficient of student-teacher ratio actually declines by almost half when you include additional factor. We also said that the interpretation of coefficient in multiple regression model, in this case, negative 1.1 means that what is the effect of student-teacher ratio on test score controlling for percent English learners. This is similar, what we're doing in multiple regression model here is similar to our previous lecture where we are comparing the effect of class size within the same percent English learner districts. So in the previous lecture, we showed that, for instance, we were fixing the percent English learner in each district and then comparing the test score of small and large class size district. So say the small class size district had 620 as a test score and large class size district has 600 as a test score. And looking at districts with the same percentage of English learners, we subtracted these numbers to interpret that this is the effect of student-teacher ratio or class size on test score controlling or fixing, holding percent English learner constant. So multiple regression model is doing exactly that. The coefficient shows that the fact that the coefficient declines when you include additional variable, percent English learner, shows that our previous model, simple linear regression model, was wrong. It was actually overestimating the effect of student-teacher ratio. So in other words, because the absolute size or absolute term 2.28 is greater than 1.1, it's showing that in the previous simple linear regression model, we're overestimating how much impact student-teacher ratio has because we omitted the factor percent English learner in the model. And we can say that the previous model, the simple linear regression model, suffered from omitted variable bias.